Today we'll talk about second order equations, a special case of them which are homogeneous and linear. We talked about this kind of equation at the beginning of the semester. It's like this: a function of t only times the second derivative of y, the dependent variable, plus a function of t only times the first derivative of y plus function of t only times y is equal to 0, where a2 isn't 0, where it's not a second order equation. It's called a linear second order equation for y as a function of t. Now, there's a couple big points I put up here at the beginning that we're getting to. But it turns out that if you have any two solutions to this, if you take a constant times one plus a constant times the other, again you get a solution. Which means also if you have three solutions, you can take plus a constant times another plus a constant times another just by using this recursively. You can get any linear combination, we call it, of solutions is again a solution. If there's just two of them, we call this a superposition of solutions. So for a second order equation, how do we find all the solutions? It turns out that if you take two independent solutions, y1 of t and y2 of t, often called linearly independent solutions, it just means for two functions that one's not a multiple of the other, then this actually turns out to be the form of all solutions. If you let C1 and C2 be arbitrary, all solutions can be written as a constant times one solution plus a constant times an independent solution. Every one of them. Much like when you're in the plane, you can take a constant times one vector plus a constant times an independent vector, one that doesn't point along the same line, and span the plane with two vectors, get to any point in the plane by taking a multiple one vector plus a multiple of the other, just so you can get to any solution in the solution space of a linear second order equation by taking a constant multiple of one solution plus a constant multiple of the other solution, thinking of these as vectors. It turns out in the abstract mathematics sense, these are vectors in a vector space of functions in graduate school and so forth. So it's actually really the same concept, just with harder proofs. So here's the first one we said, the superposition principle for second order equations. If y1 and y2 are any solutions whatsoever of a second order homogeneous equation, it's one like this, it has to have 0 on the right to be homogeneous, right? And then non-homogeneous will say if you allow a function of t on the right, then remember that was a general linear equation of second order. So if you have any two solutions of a homogeneous linear equation, then an arbitrary multiple of one plus an arbitrary multiple of the other is again a solution. We call that the superposition principle we stated up above. Here's the proof. You simply plug it in. You plug in y equals c1, y1 plus c2, y2 with the assumption that y1 and y2 are any two solutions. And if you plug it on the left side of this equation here, then you get this. You get a2 of t times second derivative of y plus a1 of t times second derivative of y plus a0 of t times the y on the left. What is that equal to? Well, it's equal to, right? Remember the second derivative of c1 y1 plus c2 y2 from calculus is the derivative of the sum is the sum of the derivatives. And then actually you can pull c1 and c2 out of here too, right? You can pull those out of the derivative. Similarly here, the first derivative of c1 y1 plus c2 y2 is, well, derivative of the sum is the sum of the derivatives, right? And so you've got this. And then you can pull the constants out. Well, when you pull the constants out and regroup, we'll put all the things with c1 here and c2 here, algebraically that becomes c1 times this plus c2 times this. But now, and so this is an algebra step, after having pulled the c1 and c2 out. But now, the assumption was that y1 is a solution of the differential equation. If so, this is the left side of the differential equation. If y1 is a solution, it has to be the right side, 0. Similarly, if y2 is a solution, this has to be equal to 0, right? This was the left side, and the right side was 0, so you replace that with 0. So you have c1, 0 plus c2, 0 is 0. So it shows that the assumption that y1 and y2 were solutions, also c1, y1 plus c2, y2 is a solution. Superposition principle proved. And so here's an example. Suppose I just plug in to see that t squared is the solution of this. Remember we just plugged in before, second derivative is 2, so 2 times t squared. And then the first derivative is 2t, so minus 4t times 2t is minus 8t squared. 4t squared minus 8t squared Let's see. No, it was 2t squared, I'm sorry. Derivative here was 2t. 2t times, the derivative here is 2. 2 times t squared minus 8t squared, right? 4t times 2t, plus 6t squared. So 2t squared, 2t squared minus 8t squared plus 6t squared, you add that all up, oh, it gives you 0. Sure enough, t squared is a solution. So you can plug it in to see it. Similarly, you can plug t cubed in and you'll find it's a solution. I automatically know that any multiple of t squared plus a multiple of t cubed is also a solution. So I can take 2t squared plus minus 1 times t cubed. That must also be a solution by the superposition principle. So that's a very important principle of linear homogeneous equations only. Don't assume that for other equations. It also works for other order linear homogeneous equations. You can try it in first order or third order or something. Now, here's their graph. So you have the graph of t squared. Oops, t squared is the blue one. And you have the graph of t cubed. And then this is 2t squared minus t cubed is the other one. And it's automatically a solution because that's what we call a superposition of these two, or a linear combination of two functions. Now, we'll say that two functions, y1 of t and y2 of t, are linearly independent, or just independent on an interval I of t values. If there's no expression, c1y1 plus c2y2, that's 0 on the whole interval, unless c1 and c2 are both 0. So the only constant c1 and c2 you can put here that makes this function, this superposition 0 on the whole interval, is we can put c1 and c2 both 0. Then we'll say they're linearly independent. And if you can find two constants not both 0, then you say the two functions are linearly dependent. All right. Important note here. This equals 0 on the whole interval with c1 and c2 not both 0 is equivalent to saying that either y1 is this multiple of y2 or y2 is this multiple of y1, which means linearly independent for two functions. This simply means that they're not you don't have one a multiple of the other. That's all it means. All right, so here's an interesting result. y1 equals e to the t, y2 equals 2e to the t. They are linearly dependent because this one's just twice this one, right? y1 equals e to the t and y2 equals e to the 2t are independent though. If you take a number times c1 times this one plus c2 times this one, and you want that to be equal to 0 at a whole interval, not just at a specific value of t, then that means by subtraction that c1 e to the t is minus c2 e to the 2t, and then you can divide by e to the t, and that says c1 is equal to minus c2 e to the t, which means, well, divide by so the only way you can make these equal is to make c1 and c2 both 0, right? Because this side isn't constant and this side is. You can't make a non-constant equal to a constant unless both of these are 0. Or you could write it equivalently that in order for this to be 0, you can divide by, with c1 and c2 not both 0, divide by minus c2, and that says that e to the t is minus c1 over c2, a constant, not true, right? So this equals 0 has only the solution c1 equals c2 equals 0. Therefore, e to the 2t and e to the 2t are linearly independent. Well, that's kind of a hard proof, isn't it? Who wants to do that every time? There's a fast check. You can use something called the Wronskian. If you're given two functions, y1 and y2, you put those on the first line and y1 prime, y2 prime on the second line and take a determinant. Remember from early calculus, the determinant means take this times this minus this times this. So y1, y2 prime minus y2, y1 prime. And if that is equal to 0 at some point in the interval, there's this nice theorem that says, well, let's first say that if you have two differentiable functions not necessarily solutions of the differential equation. And the Wronskian is not zero at some point, they're automatically independent. So if you just take that determinant, find some t for which their Wronskian isn't zero, then you know they're independent. But it's even stronger than that. Famous mathematician named Abel figured out that actually, if you have two differentiable functions that are solutions of a differential equation, a homogeneous differential equation with continuous coefficients like we're interested in, then either their Wronskian is zero on the whole interval and they're dependent, or the Wronskian is non-zero on the whole interval and they're independent. That means you don't have to check every t, you just check one t in the middle of the interval. If the Wronskian's not zero, they're independent. If the Wronskian is zero, they're dependent, but that only works for solutions of a second order linear homogeneous equation with continuous coefficient functions. All right, here's the example we had before. T squared, t cubed. Maybe I don't know their solutions of a differential equation, and I just wonder if they're linearly independent functions. Well, I can put them in the Wronskian, t squared and t cubed, and their derivatives down here. I compute the Wronskian. This times this, minus this times this, here it is t to the fourth power. And I observe, since there is some t for which t to the fourth isn't zero at that point, right? For instance, t equals 1 or something. These are linearly independent functions on any interval that includes t equals 1. And actually, you could say, suppose I want to show these are linearly independent on the interval t going from -1 to 1. Well, I know that t equals a half or something. The Wronskian is not zero. Since it's not zero at some point, these are linearly independent on the whole interval, on the interval. This one I think I'm going to skip. Here's Abel's theorem that we just stated. If y1 and y2 are solutions of a homogeneous linear differential equation, we'll put it in standard form by dividing through by the lead coefficient, a2 of t. So that this is p of t is the a1 over a2 and q of t is the a0 over a2 from the original form. So, which you can do on any interval where a2 isn't zero. So if you put it in standard form like this, and p and q are continuous functions, then the Wronskian turns out to have this form, and e to anything isn't zero, and there's some t0 in the interval that makes this true, and you can show from this result that actually, here's the proof, and I won't go through the proof, but for math major, maybe you want to look at it. You get this corollary because of Abel's theorem that it's equal to the Wronskian at a particular point times e to the integral. That if y1 and y2 are actually solutions of a linear homogeneous second order differential equation in standard form with p and q continuous, then I'll restate it again. They're either independent if the Wronskian is not zero, or they're dependent if the Wronskian is zero, and the Wronskian is either not zero in the whole interval or zero in the whole interval because of Abel's theorem. All right. So here's an interesting problem. Suppose I'm solving y double prime plus y equals 0. There's a second order differential equation. And I happen to know by plugging in maybe that sine t and cosine t are both solutions of this. Are those independent? Well, I put sine and cosine in the first row. It doesn't matter the order. I'll put cosine first. And then the derivative of cosine is minus the sine, derivative of sine is cosine, and I take the Wronskian. It's cosine times cosine minus sine times sine is cosine squared plus sine squared is 1 by trigonometry theorem. Since the Wronskian is not zero, these two functions are independent on any interval whatsoever. Which means, since they're solutions, c1 times this times sine plus c2 times cosine is a solution on whatever interval you want. Here's another one. T and t squared are solutions of this differential equation. So maybe I can check to see if they're independent. Here's t and t squared and their derivatives. The Wronskian is t squared. Since it's not zero, these are independent functions, but t and t squared can't be solutions on any of a second order homogeneous equation with continuous coefficients on any interval that includes t equals 0. Why not? Because the Wronskian is 0 at that point. if there were solutions of such an equation, they would be non-zero on the whole interval or zero on the whole interval. So they might be solutions on some interval that doesn't include zero, but they're not solutions of this in standard form, divided through by t squared, on an interval that includes t equals 0. Interesting, huh? All right, so now here's a big theorem. What we're trying to lead up to is how do we solve these things, right? We've been talking about we can show their solutions by plugging them in, any linear combination, any superposition for linear combination to them. Any linear combination is, again, a solution. And we can show when they're dependent or independent, so what? So this, given independent solutions, y1, y2, of a homogeneous linear second order equation in standard form, where you divide it through by the coefficient, with continuous coefficient functions p and q, the set of all solutions is this family of solutions, c1, y1 plus c2, y2, where y1 and y2 or c1 and c2 are arbitrary numbers. This is all the solutions you can get. It's just like you can span a plane with two vectors, you can span the solution set with two vector functions, actually. This is a wonderful theorem. This tells us a nice way to solve differential equations. All I have to do for equations of this form is find two independent functions and write c1 times the first plus c2 times the second. I've got all the solutions. Now if I get initial conditions, I can determine the arbitrary constants in there for the, and get a unique solution for those. But this gives all solutions to the differential equation, an infinite number of them. Here's an example. d squared y dt squared plus 40y dt plus 3y equals 0 has the form of, right, linear second order homogeneous equation in standard form. The coefficients 4 and 3 are constant functions, so they're certainly continuous. They're horizontal lines, right? And we notice by plugging in that e to the minus 3t and e to the minus t are solutions. What's the general solution? Well, we'll check the Wronskian. E to the minus 3t, e to the minus t, they're derivatives. The Wronskian comes out to be, right, this times this minus this times this is 2e to the minus 4t. E to anything isn't 0. The Wronskian's not 0. These are independent functions that are solutions to this equation. By our theorem, this is the general solution, the form of all solutions, y equals c1 e to the minus 3t plus c2 e to the minus t. That's all solutions to this differential equation. Just a matter of what c1 and c2 do you want to pick. Here's another one. This one has non-constant coefficients. If it's in standard form here, p of t, this coefficient is minus 2 over t. Q of t is 2 over t squared. These are not continuous at t equals 0, right, because of the division by t and t squared. But on any interval that doesn't include t equals 0, that would sound like the example we did, we can write the general solution of this as c1 times this solution plus this c2 times this one, because their Wronskian we found wasn't 0 on any other interval. So here's the general solution to this differential equation, c1t plus c2t squared on any interval that doesn't include 0. That's where it's not defined. How about that? And so here's the geometrical note that is like this plane. This is pretty easy homework. Just plug these into the Wronskian, that determinant, and show that the functions are linearly independent by showing the Wronskian isn't 0. And then when we have two solutions that are linearly independent to such an equation, the linear equation with continuous coefficients in standard form, we call them a fundamental solution set because we can write the general solution as c1y1 plus c2y2. So show that these two functions form a fundamental solution set by plugging them in to see their solutions, putting them in the Wronskian to see the Wronskian's not 0 on this interval t greater than 0. Same kind of thing with this one. Sinh and cosh, the hyperbolic trig functions. Remember, derivative of sinh is cosh, derivative of cosh is sinh when you do this one. Easy homework set.